Good to have you all here.
Hi, Siddharth.
Hi, Siddharth. And,
are we audible and visible?
Yeah, I can hear you guys. Hi.
So I'm Shreyas, this is Nakul, and these are some of the first year students that we have.
Hello.
Talk. And a lot of people are joining.
A lot of people are joining in.
I will be joining online as well.
Mm-hmm.
So, I'll briefly introduce Divyansh and Siddharth to all the attendees here. So, Siddharth is a PhD scholar at TU Delft, and Divyansh did his master's from University of Gdansk, and they'll be talking about how PhD admissions work and their work that they have done in universities abroad. And we hope that it's an enlightening experience for all the people, and they get to know how to maybe think of a career in quantum computing, and if they are looking to apply in foreign universities, how they could change their applications and how they could write their application. So without further ado, I'd like Divyansh and Siddharth to start. Thank you.
So shall I share my screen now?
Yeah.
Okay, perfect. Okay. Is it visible now?
It's visible.
Perfect. So yeah. So I was told here mostly first yearites and second yearites would be here. So all of those who are quantum curious, I just wanted to tell you about what I've done as a master student at my university in quantum information tech. So yeah. So a brief history about mine. So I did my master's in physics from BITS Pilani campus. In 2020, I passed out and then briefly joined the IT sector working as a data scientist and realized it's not for me, I guess. So then I went for a master's in quantum information tech in Poland. I will tell you briefly about how I got there. I was also a researcher at ICTQT. This is like a mecca of quantum information theory. So a lot of theoreticians were there, and really deep stuff was worked here. So yeah, I think you should check it out. So what I will talk about is why quantum. Why should you be interested in quantum in the first place? You are first year, second year students. You should, you might want jobs, and then you should go for computer science. But why quantum? Because and then I will talk about what is quantum. So yes, why quantum, and then what is it, and then how to get into it. So okay. So why quantum? What is the motivation? So in the 1990s, it started to emerge that the theoretical framework of quantum mechanics, which emerged in 1920s, was very useful for some applications in computation. A very famous case was Shor's algorithm, basically quantum Fourier transform. And this revealed to us that, okay, there's an exponential speed up in certain tasks. And this is what kind of started the field to make a quantum computer to break RSA using this. So this can make a lot of security systems vulnerable, and that's why the race of quantum computers started. There are other advantages to using quantum mechanics, combining it with computation to, for example, Harsh Grover, Love Grover, he discovered that you could quadratically speed up the unstructured search algorithm. And that's a big deal. Imagine Google doing searches all the time. You could quadratically speed that up. So this was another impetus to work on quantum computers. Another one was by the famous Richard Feynman. He said that nature isn't classical, so we shouldn't simulate using classical computers. We should use quantum mechanics to simulate systems which are quantum mechanical in nature. Yeah, so he was a big proponent of quantum simulations, and that's actually where I started. My project in BITS Alumni was involved in classical simulations of molecules, and I realized that it's so slow as the molecule size scales. It used to take like days for my laptop to work out. And so I realized that, okay, if you have to work with any meaningful sized molecule, the scalability is really bad for those simulations. Another is, to keep secrets. Quantum key distribution is a major emerging tech, and I believe it would be the first one to get commercialized. In this case, basically, you keep your communication system secure by using quantum circuits or quantum channels, in which if you measure anything, there will be an information leak to the Eve, and it would be detected by the sender and the receiver. It's a very active field, and I would really suggest you to check it out because it's not theoretically as demanding as maybe quantum foundations, as I would speak about later. Okay, another very ignored field or application of quantum technologies is quantum sensors. So this is really one of those things which is not in the limelight, but really producing results. For example, this one, we could measure magnetic field very, very finely with using quantum sensors, and it gives us abilities like far more a far more resolution in brain MRIs. So it has vast applications, and it's been worked upon in US and Europe quite extensively. Yeah. So okay, now you know why you should work on it. But what is it? Why does it work at all? Why are there such advantages here? So I would like to give you like an analogy I made up. It's quantum cricket, let's say. Okay, so I guess every one of us watched on Sunday. So at the beginning of the match, if you were just sitting at your home and you were busy, let's say, and you could not watch the match, then you would just check the score initially and say, okay, there's a 50% chance of India and Australia winning. So in quantum mechanics, we would use the concept of superposition to represent this. And the probabilities with which the winning streak would be the square of its amplitudes, as you can see. It's called Bond rule. Okay, let's not get into technicalities. Okay, so you're sitting here at home, you just saw the score, and you're like, okay, India and Australia will win with 50% probability. You close your TV and they just sit around. Then you see a transformation happened. Maybe Kohli left a catch, and that then reduces the probability of India winning. And then okay, what can you do? Then you switch on the TV again afterwards and see that, okay, there are three. There are three outs. So now the probability of India winning maybe is higher. And then you're like, okay, let India win. I'll see in the end. And apparently, no. So I just wanted to give you an analogy of how superposition works. It's not quite an analogy here, but I hope you get the sense of, in quantum world, two states can exist at the same time, and the answer is probabilistic according to the state. Okay, this is the first property, the feature of quantum world, which makes these advantages possible. What are the other ones? So let's say you have this superstition that if I sit on a chair and watch the match, then India would win. While if I'm comfy on my sofa, India would lose. So now you believe that if I sit on the sofa, the Australia would win. And if I sit on my chair, India will win. I'm sure a lot of us have such superstitions. So you sitting on your sofa in Goa would make India lose in Ahmedabad. So this is an action from a distance. And this is like an analogy to what happens in quantum systems called entanglement. So Einstein called it the spooky action at a distance. I'm sure you guys have heard of this. And this is the second feature, which is very important. And I will explain why this is very important in quantum computation. All right. So there are other features like this, which form the field of quantum foundations. This was extensively worked at ICT-QT. This involves things like resource theory. So how does entanglement act as a resource? And then we go deeper into concepts of contextuality, which see the difference between, okay, the measurement set and the prepared state set. Like you can get really deep into it. And then there are deeper concepts which connect to quantum gravity, such as indefinite causal structures. And you're trying to generalize quantum theory itself through things like operational probabilistic theory. So any of you who are interested in pursuing deep mathematical, theoretical physics should look into quantum foundations. And I would suggest ICT-QT is a really good place for that. Yeah. So how does a quantum computer work? I'll just give you an overview, a kind of analogy with classical computers. So in classical computers, what we do is we use bits. In bits, the state is either 1 or 0. And then we use a circuit to transform those bit range, the bit register, to another bit register, to a wanted answer that we want. The transformation, how we do that is called an algorithm. Yes, and then we measure those final bits, and that is it. We get the answer. How is quantum computer different? So the way it works is very similar. We will have a set of qubits now. A qubit would be a superposition of two states, as I discussed before, superposition. And entanglement comes here because to make this register of, let's say, in this case, 8 qubits work coherently with each other, we would need to entangle them. And entanglement is a very fickle phenomenon because any measurement to the system would collapse the wave function. And so you need to keep it isolated. All of these hardware stuff, Siddharth will tell you better because he's working on hardware. So now you have this register. All the qubits are in superposition and entangled. Okay. So now you transform them using these specific, these very specific kind of transformations called unitary transformations. What this unitary transformation does is basically preserve quantum information, which is necessary till the end. Otherwise, you will be leaking information from the circuit. And so quantum circuits do this unitary transformations and give you transformed qubits. And then you measure those, and with some probability, you will get your answer correct. And the point of making a quantum algorithm is to make those probabilities as high as possible for the correct answers and low as possible for the bad answers. This is done by a concept called interference. So when you interfere two states, the destructive interference causes the bad answers to go away, while the constructive interference, through constructive interference, you want your answers, the answers you want to add up so that the probability of them coming up would be pretty high. Okay, so this is just a basic analogy of why superposition and entanglement is required. Yeah. Now I've come to my thesis. So I'll tell you what I worked on. I worked on multipartite systems, multipartite entangled systems. So rather than just taking 1 or 2 qubits, you, let's say, take n qubits and you entangle them somehow. But how do you know which one is entangled to which? How do you quantify what kind of entanglement would be there? Because it's a very important resource to know that how powerful that entanglement would be to compute, to use it as a compute. Yeah. So the way it works is this is a complicated function which needs to be optimized to find this value. So I basically use this entanglement quantification quantity, and it needs to be optimized. And my thesis was really to apply gradient descent to it, find its gradient using some matrix calculus, and then get the bounds, the lower bounds. Yeah, and another of my work involved more lab work, but Yeah. So in this, what we were doing is using, if you know polarizers, polarizers, when you hit them at 45 degrees, can either go this way or this way. The people who have studied optics might know this. So we use two polarizers, which are either aligned or at 45 degrees. And then, given what kind of arrangement is there, we can either produce random numbers or very deterministic numbers. And we have put it in such a way that you can detect if the numbers are completely random or if there is some like order to it. Because if there's order to it, if it's not completely random, the thing that I told you about quantum key distribution, it requires completely random numbers because there is no information in it. But if it is not completely random, then the eavesdropper can attack using, these are called random number generator attacks. So it's very necessary to make these things. And we were trying to make this schema work. And what happened was we were trying to, it's a funny story here and a lesson that we were trying to see, we were trying to work with CQT in Singapore, the lab that was working with us. And what happened was the PhDs there who were supposed to work on it left. And so our work was in Lingo for a year. So, and now we are building our own lab to work on it. So I guess the lesson would be that don't expect your research work to just go smoothly and everyone would agree to work on, would be there afterwards. There's a lot of logistics involved, which is behind the scenes. And when you take up PhD, you realize, okay, I'm doing a lot of logistics work, a lot of management between professors and PhDs. And this, you realize you didn't sign up for this. But this is an essential part of research. And I would say, keep this in mind when you try to apply. Okay. Now, how to get started? Basically, be very good at linear algebra. That is the core mathematical foundation of if you want to get into the theory part. And just to have an understanding, you need to have a really good foundation in linear algebra. So just to give you an example, the example I gave you before of India-Australia match, this could be represented as a matrix and then transformed using unitary matrices. This is a very simple example, but all my research was really matrix calculus. And you need to really be aligned with how matrix transformations work. So I would say take your linear algebra courses very seriously. And honestly, even if you try to get into computer science and AI nowadays, linear algebra is the mathematical tool of the century. So just get strong at that. Secondly, if you want to get into this field specifically, a really good basic resource is this book by Nielsen and Chuang, Quantum Computation and Quantum Information. This will give you an overview of the field. So it will give you the basics of the first 3 chapters, and then it will give you basics of the quantum algorithms in the next 4 chapters, and then quantum information is there. So it will give you a roadmap of where you want to work, depending on which chapters you found the most interesting. So for me, quantum information chapters, chapter 10, 9, those are very interesting. So that's why I applied to ICT-QT. Because think about it, somehow or the other, classical computers are working on information computation, but quantum computers are doing it in a completely different way. Same information, same computation, but way faster. How? That was a question that really intrigued me. That is one thing, to know the map of the field. Secondly, if you want to get slightly deeper into quantum mechanics, to think about more theoretical aspects, for example, the paradoxes, all the paradoxes in the field, there are many. If you want to work on, they're very interesting thought experiments. You should work on studying this book. This will give you the good basics. It builds up slowly as a story, and it's a beautiful book to read. Yeah. And thirdly, I would suggest that you start quantum coding. So there are many platforms. I think this is IBM Qiskit Summit. So I have never worked with Qiskit, but I've heard it's pretty good and its library is pretty expanded. I used to do these hackathons by Penny Lane. Fun stuff. Like really, they give you an example, they give you a question, and it's like lead code for quantum algorithms. It's really fun stuff. You should try it out. Secondly, try like simulation softwares. For example, the QTEP. This was instrumental in my thesis. So there are tutorials on how to simulate open quantum systems or Rydberg atoms. Very interesting stuff. So working with these problems, it would give you an intuition on how these things actually work. What part? Why does this gate work, and why should I put it here? This will give you. It will build up an intuition. That's the best way I could put it. Yeah. So just keep on the quantum hackathons. Yeah. Yeah. So I would say that's all. And yeah, and along the way, actually, if you do apply to these places, one suggestion would be that keep your GPA high enough, because it's just a filter. It's not like you have to have 9, but keep it high. Then do projects, do these coding projects, show your interest to the professors there. That's all they care about. Because when I applied, what they really care about is the letter of recommendations, which you can get from your professors, and your basically motivation letter. Why do you care to work in this? We could be doing something else. Why this? Why us? The question you should answer there is, why I care to do this? Why me? Because I have this experience, I have this interest, I want these questions answered. And why am I choosing you, the professor? So you should really deeply work on knowing your professor, why to choose him. Because even at master's level, my thesis work was so intense that you could see that if the relationship between the professor and the student was not good, it could really fall apart. So talk to PhD students, talk to the professors, people around the professor, to know really how he is. That's the one thing. Reach out to everyone. And along the way, actually, if you do pursue this, you will have a lot of fun. You meet a lot of very smart people from completely diverse backgrounds. You get to have real fun, like stuff you wouldn't imagine you would be able to do. So yeah, I encourage you to get into this, and I hope you enjoyed this. Thank you, and Siddharth, you could take over from this.
Thanks a lot, Divyansh. That was
I really like the entanglement analogy that you gave about the India and Australia match.
Yeah.
That was really interesting.
Yeah, I mean, I realize it's not quite an analogy, but I tried to connect it to. Yeah.
Thanks.
Okay.
I think Siddharth can take over.
Yeah, I'm trying to share my screen actually.
Yeah. No worries.
Can you see my?
Yeah, the screen is visible.
Do you see the whole screen or just the PPT?
The PPT. I mean,
it's visible.
It's visible. Yeah. It's the whole screen only, I guess. It's not on slideshow, right?
Yeah, that's what I'm trying to. Wait. You see it?
Yeah, it's visible. It's completely fine.
Okay. Yeah. So, Divyansh gave you some introduction about what he worked on, and I have been in this field for almost 4 years now, considering my master's thesis as well. So it has been a long time, and you guys are just starting. You guys are in your first year, so I imagine most of you didn't have introduction to quantum mechanics yet, or maybe you will have, or some might have done by themselves. So I haven't included any heavy concepts as such. I just wanted to take a step back and give an analogy of what development of technology can do. So let's just take an example of optics. So in the past 200 years or so, we figured out the basic mathematics and the basic physics behind what is happening at the very basic level for optics, like simple reflection and refraction, total internal reflection or diffraction. So all these things are pretty much familiar to all the people, and we know how they work. But it took some time. It took like more than 100 years to apply these things to something physical. So, for a simple concept of reflection, you can think about a simple mirror, but then you can also think about a telescope which is operating in the space. So, both of these things work on the same principle. If you think about refraction, you can think about your image in the swimming pool, but you can also think about lithography machines, how they work, and how they process our chips today. If you think about lasers, okay, laser is still not very simple, but when it was developed in 1960s, it is just the bunch of energy coming in one go, but the applications were still not developed. And now you can see people use laser cutting, people use laser for a lot of sensors, people use laser for communication. So there's a lot of different applications which are coming up. And total internal reflection you can see in fiber optical cables, diffraction you can see in the CDs, although CDs are getting obsolete now. But all these technologies were not developed in one day, but the mathematics which was involved behind this and the simple laws. uh, by laws I mean basically you define a certain boundary condition, and you define a certain physics, and based on that you can make a lot of systems. And these applications are the systems which you develop as a consequence of these laws. uh, and this is the case for optics, and we all know the basic mathematics and the application. That's why it's simpler to understand what has happened in this field. But similarly, in the past 100 years, the laws of quantum mechanics are also changing how we develop newer systems for the next generation. So it's not just about newer systems, it's also about what kind of applications we can develop. And I'm not going to talk about what uh, quantum mechanics has, like things like quantum entanglement or teleportation or all these things. You can read about themselves. You can read about themselves, but these applications need a physical system to be implemented on. You need a physical system on which you can work out these laws, and you see that whatever you had thought in mathematics or in your equations is being replicated on your system. So again, taking an analogy from optics, something as simple as reflection has losses. You can have a perfect, let's say, some power coming in from one angle, and then maybe the whole thing doesn't bounce off in the same direction, or maybe the same power doesn't go off. There is some transmission, there is some absorption. So all these things are imperfections in your system which you are trying to engineer. So in the coming years, or in the coming 20 years, the field of quantum engineering will spring up, and quantum computing is one aspect of it. So you have to first engineer a system which will enable these quantum laws. Then you will be able to do quantum computing on top of these things. So first, the field of quantum engineering is coming up within the next 20 years. And what it means is basically you have to make these systems which follow your boundary conditions, which follow your equations. So now, uh, at the very core, what is what is like quantum systems is basically light matter interactions. What you have is, let's say, some matter. In this case, just a two-level atom. That's the very basic atom you have. And when you add a single unit of light, which is called the photon, to this, you basically do an absorption of the photon. If it is the right energy, your atom will jump into a higher state. And then if you again de-excite the system, there will be a release of light. So this is simple light matter interacting with each other. And here the 0 and the 1 state is basically the ground and the excited state of the atom. This is very basic physics which we have studied. But turns out we can use these things for very interesting applications. So in the 1970s and 80s, what people started building were basically very high quality mirrors. So what you see here is, yeah, okay. I'm unable to find the pointer. Okay, anyways. So here are two mirrors in between which you have vacuum. So you make a chamber out of which there is like two very high quality mirrors. You put an atom in this vacuum, and then from outside you are inputting some photons. So what you are making sure is that this photon has the same wavelength for the excitation of the atom. And on the output side, what you will see is that the photons are being released, which come from the de-excitation of your atom. So now based on this input and output rate, you can calculate how many photons are getting absorbed in the atom, or how many of these photons are getting out of the atom. And obviously there are always some losses. So if you have some loss for the mirror kappa and some loss from the atom directly gamma, you can interpret some properties of the system. You can say, okay, the atom is absorbing the photons at a certain rate, and it is emitting the photons at a certain rate. Uh, if your mirror quality is higher, let's say if you are able to make even better mirrors without any losses, you will see that the kappa decreases, and you can also somehow manipulate gamma. But this is a natural atom. There is physical limitations put in by nature that how much properties you can change. You can only change your mirrors. You can only change how many photons you're giving in and how many, but you can't really change the properties of the atom. So people studied a lot of these systems in 70s and 80s and figured out, okay, we have reached a limitation. And then people came up with the idea that what if we can make an artificial atom and replicate similar behavior and try to see whether we can study quantum systems which are synthetically made. So people were studying natural quantum systems, and now people are studying synthetic quantum systems. And then that is how the field of quantum engineering evolved in the 90s and 2000s. And now we have reached a certain point where these properties are good enough to qualify for computation. So people are saying, okay, so the losses have gone down significantly, and maybe now we can use these for the applications of quantum computing, which have been in development and theoretical field till now. So I work particularly on on superconducting qubits. But basically, what is a qubit? A qubit is a two-level quantum system. We use the 0 and the 1 state to encode the information in the basis states. What you need other than just a qubit is that you need interaction of the qubit. Now, how should the interaction be? You need interactions with other qubits to make a system, and you also need interaction with the environment. Otherwise, your qubit is useless. If you have a very good qubit, you can have it in vacuum, but a qubit in vacuum is useless to you because you can't use it for anything. So you need some interactions, but these interactions bring in the decoherence. and these are basically losses. And as an experimentalist, what we do is we are trying to engineer these interactions and we are trying to fight the decoherence. So these are our performance matrices. If we can increase the interaction without losing too much or without having too much decoherence, we are making a better system. And that is what the whole field is trying to do at the moment, is build multi-qubit systems uh, and have less decoherence. Now the question comes in, how many qubits do we need? What is physically required? So then the question is, how many qubits do you need for something practical? And that can be defined, that cannot be defined directly. Like there are indirect ways of answering this question. Is some people say we need 10,000 qubits, some people say we need 1 lakh qubits. It depends on the application which you are trying to do with your qubits. Probably you can do something useless with 6 qubits. But to beat your classical computer, you need a lot more from the current hardware. Maybe 10 years down the line, we may not need as many qubits because the decoherence is our current limitation. Down the line, we will have better materials. So I work on superconducting qubits. And to give a basic introduction on superconducting qubits, what we do is we write a Hamiltonian. Hamiltonian is like a description of the energies. In our high school, we write the total energy for the system as kinetic energy plus potential energy. Where this comes from is, like, if you go deep into classical physics, you will figure out that okay, this energy description mathematically can be written in Hamiltonian formulation. That is what it is called. It's basically equations in mathematics for your energy. And a superconducting qubit circuit has 3 elements. So we are making these circuits using 3 elements, and then we write their energies. So first is capacitive energy for a simple capacitor, then is the inductive energy for an inductor, and then we have something called as a Josephson junction, which has the energy relation as this. And these are basically simple electrical components. And then you make these circuits, and then you figure out what will be the effective property of this circuit based on how these components are arranged in the circuit. And it is as simple as the electronics, like the transistors and basic stuff. And you also have to think about the common sources of error for these qubits. So obviously for a capacitor, it will be stray charges. For an inductor, it will be some stray flux or magnetic field. And for a Josephson junction, it is generally the material defects. So we make a junction using aluminum oxide barrier. And when you think about it, there could be at the very nanometer levels some oxides left in the system, and these oxides can create stray dipoles. And when you use this circuit, it will basically this dipole will change the properties of your system. So this is getting too deep into the material chemistry, but these are the common sources of error. So now what we are trying to do is uh, first is make these circuits, but also at the same time mitigate these 3 common sources of error. And so the most basic example for a superconducting qubit, which is widely used and today is Transmon. It is used by Google. It is being used by IBM, and this is what they are using to make their big quantum processors. And in a Transmon, what we do is we put a simple junction and a capacitor in parallel as the circuit diagram. Then we write the Hamiltonian in quantum formalism. Again, you will have to learn some amount of quantum mechanics to understand what I'm talking about, but it is as simple as writing the energy equation for electrical circuit. That's all. The names are different. And once you solve it, you will see that you get like like a distributed harmonic oscillator. What it is basically when you attach a mass to the spring, you can see it oscillates. But when you think about it at the quantum level, this spring mass system does not have a continuous energy spectrum. It has either zero or some higher state and then higher states. Similarly, this transmon also has a spectrum where you have the zero energy, and then you will have some jump, and then you will have one energy, then you will have some jump, and then you will have two energy. So this spring mass system analogy works for this electrical circuit, and this electrical circuit is as simple as a capacitor and an inductor in parallel as well. And what you see is that you get some levels here, which is similar to an atom now, but we need to only use 0 and 1 for our qubit. So this is how we encode information using these two levels. And I work on another variant of the superconducting circuit, which is called fluxonium. Again, I won't go too deep because this will be a long talk otherwise. And just giving a basic touch of what the work involves. So the other thing is which the material chemistry, the fabrication, the design. This is what I do from day to day. So what I do is basically take the properties I need from the system, decide what energies I need. Based on those energies, I design the capacitor plates, I design the inductor, I design the junction. And what you see here is a scanning electron microscope image of the junction. The junction is basically two strips of aluminium on top of each other, and this is 150 nanometer. So this is what I do. I do fabrication in the clean room. I make like a long array of these aluminium depositions. I connect it to the circuit, and this is when I zoom out, this is a qubit. Like it is as simple as a capacitor plate lying in 2D. So you will have your capacitor plates in 3D generally, but if you just put them in a 2D configuration, what you see in yellow is your capacitor plates, and they are connected by what I call a junction, and this junction is made out of two aluminum strips. As simple as that. So there is nothing quantum which is happening right here at the moment. It is the boundary conditions at the very low temperatures which will enable the quantum behavior, but the making of the qubit itself is not something very which you will think a lot about. It's just about, okay, I need to make 100 nanometer wide line of aluminium, and then I need to put it on silicon, and that's as simple as that. And then I need to define some shapes which will define the properties of my Hamiltonian, and then I will solve the Hamiltonian to see the energy levels of my qubit. So it is as simple as this. It is just when you try to make this thing, then you will figure out, oh, now I need to understand how this aluminium is going to fall on the silicon. Is it attaching well to the silicon? Is the thickness too much? Is the thickness too less? Is the silicon even? Is the silicon getting rough? So all these simple things, which are just material related aspects, will affect your qubit properties. If you leave it in the oxygen for 5 minutes, then the properties will change. If you leave it in, so I need to treat it with some acid to make sure that there is no oxides left on the surface. What are the exact temperature of the aluminium when I was putting it on silicon? So all these aspects then you will have to consider, and this is what goes into a PhD. And basically you will have to take care of each and every aspect of the process when you are making a qubit. And then obviously I also design and measure with my team, but my main work goes into making the qubit itself. So I fabricate a lot of chips. And this is the chip, what it looks like. So these dumbbells, the small dumbbells, what I show you here are the qubits. But what you see around this thing is the circuitry which you need to interact with the qubit. So you need some PCB on which you will stick this chip, and you communicate using some microwave electronics with your chip at very low temperatures. So you put some wire bonds, which also you will see in classical electronics. You basically, from PCB to the chip, you have some wire bonds. And then on the chip, you will have some launch pads. It is very similar. Then you have 6 qubits on this chip. And then some test structures just to make sure that our qubits are the right configuration. And then we put a resonator, which is in this yellow color, attached capacitively to the qubit and also to a readout line, which is basically what we use to see this input and output of photons. As I was giving you the analogy in the very start, that you give some photons and then the photons come out. That process happens here in 2D instead of 3D. And everything, the mirror which I showed you is basically the resonator here. So the exact shape has changed, but more or less the function is still there. And this feed line we use to study how many photons are coming in and going out. And that is what we use to infer what is happening to our qubits. That is our basically the tool, the main tool. Now this tool is microwave electronics. So you have to learn microwave electronics, you have to learn fabrication, you have to learn simulation softwares to make the right design for your qubit. So you see there are different kinds of skills in different fields which you will need to basically learn how to make the quantum engineering or the devices, quantum devices. And finally, this chip goes into a fridge like this at the very bottom. And all these wire bonds, which I showed you here, basically, these wire bonds go and at the bigger level convert into these cables. And these cables go up to the room temperature. So what you see here is a fridge in which you will keep your chip. Then there are wires which will go through different stages of cooling and then finally to the room temperature. And then at the backside in this blue is what you see as the electronics. So you see that from this chip all the way to the fridge. And this fridge is, by the way, not your quantum computer. So many people think that this is the quantum computer, but this is just the fridge which enables the low temperature to enable the quantum behavior of your chip, which you put at the very bottom stage. And now to operate this fridge also you need some cryogenic information, but many of these things have been commercialized now, so you don't have to dive deep into the cryogenics part as much, but you definitely need to understand how to control your computer or how to make your chip. All these skills are needed. And this is just for the superconducting qubits, which I am talking about. Similar things are needed in spin qubits, but there are other platforms like photonics or NV centers, which do not need as many engineering in cryogenics, but then they need optical engineering to understand how to operate your lasers, how to fine tune your optics to make sure you can do the read in and read out for your qubits. So depending on what physical system you have, your engineering requirements will change. And obviously when you work as a PhD, you work with an international group. So obviously you get a lot of different cultural backgrounds, a lot of different insights from different people. And it's really nice to work in such a group. So this is my group. And I was the first PhD in the group, specifically to understand how to set up a group from ground zero. Now the question comes in how to work on such problems, because at the end of the day, it's not a PhD, it's a problem which you are working on. And from the top of my mind, which I could think about is there's a few things which you need to do. First is the skill gap. right now you would learn some C programming, some Python programming, some uh, let's say some projects which you have done, some courses you have done, but a lot of these things maybe not necessary. The problem is you at the end of 4 years you can't know which wouldn't be necessary. So you do have to cover your topics. Uh, you should be good at scripting, that's for sure, because all these systems need you to control them uh, through a computer. So you should be decent at scripting, not very good, because I still have to learn a lot of Python. So I wouldn't say I know data structures and algorithms, but I know how to do basic scripting. Um, and just to make sure that nobody thinks that okay, anyways I'll do CS then. Not that much scripting, just basic scripting, because once you can understand what the scripts do, you can control your hardware. That's all. The other thing is basic knowledge of electronics is good. So if you are orienting yourself whether I should take an electronics course or not, electronics knowledge does help in understanding how the sensors are working, how the electronics is giving you feedback, because all these sensors and feedback loops are everywhere now. So you have to know a little bit. It's not like if you miss out on your electronics courses you will lose a lot. You can cover up pretty fast even in your PhD if you want. The other thing which I would say is the most important thing is having experimental projects as experience, not as CV point. Don't think you need points on your CV. You need decent CG. I had a CG of 7.8 when I was in my last year. After PS, it was 8, which is a different thing. Um, Not PS, sorry, after my thesis. Uh, but what you do need to make sure is that you get hands on experience through experiments if you want to work on experimental things. You need to get a taste of how to make things. Otherwise, it's almost impossible to to make things if you don't know how to make things. And for that, I recommend that you start doing after your first year or second year, even just do some internship or just sitting at home, even just make things with your hands. Uh, it's not necessary that you need to have a very good project as such. Even sitting at home, you can make things which you wouldn't think are very great or maybe great looking in your CV, but without having this insight into how things work, it's going to be difficult. Then comes in the point of the stamina of doing a project. That's why I say getting in longer projects. So just thinking about something and doing it in a week is fine. In engineering, we do a lot of uh, projects through our courses. So that's fine, but doing in a really long project and understanding how to dissect it into a simpler problem uh, every day is another great skill which you need to be good at to do a PhD or to do these things basically. If you just think about something very big, you won't be able to do it in a day. So you need to have a project stamina, I term it, basically doing a 6 month or a 8 month project. Now the question comes in whether you need a supervisor for this or not. Generally, it's good to have a supervisor in the start, but some people maybe have some intuition on how to do these things by themselves. So that's also not necessary to have a supervisor. So you can do either a design project or a SOP or a DOP in your bits. That's how I did it. I think I did 4 of these projects. That was also to cover the credits and not to just do the projects. So it was mostly to cover the credits, but don't tell people. But you should understand how to do these 4 month, 6 month projects. Then comes in if there's a possibility for you to do a thesis project. Uh, you should do a thesis on a good project. Just don't take a project because you were getting it in Harvard or Yale. and you were just basically sitting and doing some Excel work. Although it looks great on CV, but maybe you won't learn as much. So prioritize learning instead of the names. If you can get a thesis project, so I did a thesis project in Bristol, University of Bristol, on fabrication, and I got a lot of hands-on experience on how to use the tools, and that was very beneficial because I repaired a fabrication tool, and from there on I could understand how these tools work. uh, so that was really helpful. So if you, even someone's backyard, if you are getting some good hands-on experience, try to do that for a thesis. After thesis comes the question whether you have a 7.5 plus GPA, which I think is okay. 8 is better, but I I think that's fine. You don't need research papers. My first paper was published when I was in second year of my PhD. So I didn't have any research papers. But then what you need to do or make sure is that you do have something to show for, that if you have done some hands-on project, you should show what your results were. You should have pictures, you should have graphs, you should have whatever the results were, and what your contributions were and what you learned from it. And from those things, your passion should be visible, that you are not talking bullshit, you are talking like real things. uh, so that's why you should have these. And maybe you can do, like, if you don't feel confident enough to apply directly for a PhD, you can do a master's or you can do a research assistantship. I opted for a research assistantship. I did 1 year of research assistantship. I did two master's thesis. So I covered all my courses by the fourth year. In fifth year, I did two theses, one in Bristol, one in IISc Bangalore. And after that IISc Bangalore experience, I thought, okay, I don't feel ready enough for PhD. So I will do a research assistantship. So I did a research assistantship. I didn't opt for a master's because I felt like courses for me didn't never worked. I always felt that for some time I will remember something and then I will forget it. So I've done enough of that for 5 years, so I won't do it again. So I would rather do some hands-on experience, and that's why I went for a RA ship. And I think there are things which you will only learn in a master's as well. So it's not like uh, for me, I can do it myself. I can conceptualize. I can think about dissecting the problem in smaller parts by myself. I don't like taking uh, like a scripted thing for myself. But a master's is also a good way of doing it, because you will gain access to a network through which you can learn about different opportunities. You might also learn about some professors. You can meet professors in different groups, while as a RA you will only work in one group. And if you end up in a wrong group, that's not a good situation to be in. So masters is also a good option. It's about balancing the trade-offs and thinking for yourself what you want in the future. uh, and then finally is once you have done your masters or RA ship, you can jump in to solve these problems through your PhD. And many people, at least in Netherlands, uh, that's what I've seen, is after their masters they are just joining these quantum startups. Although that's lacking currently in India, and I hope that situation changes by the time you graduate. But a lot of these people are just switching to these startups and companies, and they are getting hands-on experience and working on these systems, on these quantum systems. And the other way to do that is through a PhD, where you do a PhD and then you eventually end up in these quantum companies. So the question is whether you want to directly do a PhD or whether you want to do a work experience in quantum company and then think whether quantum is good. So yeah, that's the things from the top of my head which I could think about. And yeah, thank you.
Thank
So,
you. Siddharth, I mean, it was you portrayed the pathway for anyone who is interested in the
Very interesting.
quantum computing side, and you've given every detail on what to do, when to do. So thanks a lot for that. So right now, I think we can take a few questions. There was one for Divyansh, and I think he's replied. So yeah, like even if you can answer this question, Siddharth, like what
Let me have a look at the questions. What is the questions?
what motivated you to go into this field?
Okay. Yeah. So yeah, from the very start of my bachelor's, I was interested in building things. I always wanted to work at the very edge. I thought watching Discovery and National Geographic in my childhood, I used to think I'll one day I'll become a scientist. But then when I did some projects in this astro astronomy, or basically working out a mathematics project on how galaxies uh, work in this what was it called, nonlinear mathematics framework of how the galaxies are formed and how they spiral around, and stability points and how they become unstable, all these things. I thought about it, and then I was like, okay, maybe it's not so hands-on and practical to just work in mathematics, because that's what I've done in my 11th and 12th, solving integrals. So I didn't want it to do that again. So I was like, okay, I'd rather do something experimental. And from there on, I did some internships, went to a wind turbine company, felt like this is also just following the whatever the spec sheet is saying and just doing it again and again. That was also boring for me. Uh, then I went to a scientific instrument company in India, in Delhi. That's why I say the name was Quasar Technologies, and the name was not very famous. And that's why I say that name does not matter, because what I learned from there has been very instrumental in whatever I have done till now. I learned how to build systems without having the fear of knowing electronics or coding or anything. The people there just blasted me with, okay, you have to solve this problem, do whatever it takes, whether it be scripting, whether it be electronics, and everything. So then I was like, okay, now since I have some confidence in my skills, what I want to do next is do something which is at the intersection of multiple fields and is at the very edge of whatever the humanity is doing. So that is where quantum computing came in, because it is very futuristic, or it sounds futuristic at least. It involves a lot of fields like material science, electronics, computer science, cryogenics. So you have to know a lot of different things, but you don't have to learn everything, the whole. Basically, you are jack of all trades, but uh, uh, yeah, when I say it, it doesn't sound good, but you know a lot of things about a lot of fields, and it feels good, and that's what I liked personally. So I was like, okay, this is something which I enjoy, uh, and that's what I learned in my thesis, not in my PhD. And then I wanted to decide whether I should do a PhD. So I took another thesis. I took 1 year of RA. I took time to finally say, okay, yeah, this is not going to happen this way. You have to do a PhD to be able to learn everything which is involved in the process. So if you can somehow minimize time in learning whatever you are doing, that's the best way or the best approach. But if that means you also have to do a PhD, then that's also fine. So that's how I finally stumbled upon saying, okay, multiple fields, a lot of expertise. That's why I'm doing a PhD.
I think that's a great answer. And you guys
Guys,
have
any
any other
questions?
questions? Anyone online on the meet, if they have questions, can take those. Okay, I feel there are no questions.
Okay.
Thanks.
Thanks a lot, Divyansh and Siddharth, for taking time out for this session.
Yeah, anytime, guys.
You.
I was hoping that more juniors will be enthusiastic and more juniors approach the two of us. And if they want to know more, you can also spread the word in the campus. We can also do like a physics association talk or whatever it is to
Definitely.
whatever is there to just basically if people are interested and if they want to know because I have seen at least three students three juniors of mine who have finally went after me and now they are starting their PhDs. So I feel really good that okay, people are at least whoever wants to do it are doing it. That feels good.
Yeah. I mean, juniors have some evals and timings don't sometimes.
There's a lot of
don't.
clashes with some other clubs as well, events as well. So the amount of people compared to Qiskit. But I will definitely spread the word on campus. Let's go as like really going into.
Yeah, we leave the logistics up to you. But if somebody is interested, they can come up to us.
Yeah, definitely. The purpose of the club has been this: like we set up qubits, set up 2 years back for the same purpose to get more people interested, and then
build a community around Portable.
Yeah.
I would also say we should maybe arrange some like awareness hackathons.
Yeah.
Those would just get started. Because people are looking into new things. So this would be something. I think it's the new field. It's like years would be this.
Yeah.
I think really people should get into this, and for that, even if you have to start, I'm sure BITS has the resources to restart sometime.
Yeah. So like this was part of a 3-day event, Qiskit Fall Fest, and this was the final event of the fest. And in the start, we had an introductory session, and we have made challenges also for the juniors.
Okay.
So the deadline has officially passed for the challenges. 7 p.m. was the deadline, and we'll be evaluating those. And then so like challenges were made for bringing interest of people into quantum computing. So like you said, hackathon. So we up with a hackathon, but to substitute the hackathon
last year.
Yeah, we did have a hackathon last year, but to substitute the hackathon this year, we have had challenges.
Okay.
What is? Go ahead, Divyansh. You were saying.
No, go ahead. I was just saying. I see.
My main question is, what is the demographic of the people who are joining these talks and the hackathons? Are these like CS and electronics people only, or also?
We have like some of the attendees in the last couple of events were people from Phoenix, Triple E, and mechanical as well. So there are
like Shreyas here is.
So I'm a physics plus chemical student.
Chemical
engineering.
Yeah.
So advertise it in such a way that everyone thinks that it is open for them to join in as a field. Because sometimes I feel like when you say quantum computing, then computing words is just like CS or electronics, that's all.
Yeah. Like the first session we had maths people as well, and we had physics plus mechanical people as well, and physics plus chemical people as well. So
yeah, I think anyone who knows like there's so many things to do. There's something to do for everyone.
Yeah. Very well put, actually. Thanks a lot, Divyansh and Siddharth. We hope to have a few more talks when we don't know, but I think we can figure out something out. Thanks today for taking your time out, and it was an amazing session. You gave us all the directions, like how to do, what to do, when to do, and also told us about your journey, which can act as inspiration for all of us. So thanks a lot.
Thanks a lot,
and
Good luck, guys. Bye.
Bye.